This is a story about heat. Heat in our atmosphere, our oceans, and land. When you think about it, events like droughts, hurricanes, and fires, all of those are just different ways we see heat expressed throughout the Earth system. You've probably been bombarded with a lot of intense headlines in 2020. Hottest temperature recorded here, largest wildfires there. It's been a lot to take in. My name is Lesley, and I'm a research meteorologist at NASA's Goddard Space Flight Center. So the reality is the stage was set many years ago for these events. Over the last century, human activities have increased the concentration of greenhouse gases in our atmosphere. These gases act like a blanket, trapping heat and leading to overall warming of the planet. Many of these gases remain in the atmosphere for a long time, meaning that we'll be feeling the consequences of this trapped heat for many years to come. Which unfortunately means next year is probably going to bring a lot of the same kinds of stories that we saw in 2020. But taking a look at all the different ways our planet responds to the variations in movement of heat can help us better prepare for the future. Maybe one of the most obvious ways that we saw heat this year was through fire. I know the Australian bushfires were big news last January, and when you think about it, years of prolonged hot temperatures and drought really set the stage for these fires to be more likely and more severe. With drought and heat waves, we typically see an increase in the availability of dry fuels, which leads to more powerful fires. So when you have multiple years of intense heat, it's not surprising to have significant fire events like we saw in Australia. These fires were so extreme that we saw smoke injected as high as 18 miles above the surface. That's really important because when smoke is injected that high, it can have the same type of effect as a volcano, having these very, very broad impacts across whole hemispheres of the planet. At NASA, we use computer models like the Goddard Earth Observing System to help us study how aerosols and particulate matter move through the atmosphere. So we take these models, we input real-world observations and data to track fire emissions to help understand how they're forming, where they're going, and how much of an impact they'll have on you and me. In California, heat waves have increased fire risk, and as a result, we saw a lot of synchronized fire activity. That is, many dangerous wildfires burning at the same time. And unfortunately, these types of huge fire events are becoming more and more common across the western United States. And that's a big problem. This year, Siberia also had a remarkable and active fire season. What we saw was that temperatures in the region were much higher than normal for this time of year. In fact, the temperatures above the Arctic Circle broke records in many of the same regions where the fires were burning actively. In the Arctic and boreal forest ecosystems, heat waves can exacerbate fires. And in the Arctic, you also have to factor in permafrost, which is soil that's frozen for long periods of time, and that can make the impact of fires in high latitudes even more complex. When severe fires burn in areas with permafrost, we lose this important insulating organic soil layer, which accelerates thawing, and it's potentially releasing carbon that's been stored in the soil for hundreds and in some cases even thousands of years. And you sometimes see these zombie fires, which happen when wildfires burn deep into peatlands or smolder in forests under snowfall. If that temperature doesn't get cold enough to extinguish the fire, they can continue to burn over the winter, even long after the visible fire's been extinguished at the surface. So come spring, they reemerge and they continue to burn back on the surface again. Studying what happens in the Arctic is really important because it's warming about 3 times faster than the rest of the planet. And all those aerosols and the carbon that come out of the Arctic don't necessarily stay there. They affect the heating and air pollution in much larger regions of the planet. Another part of the planet affected by heat, of course, is ice. land ice in the form of ice sheets and glaciers where we've seen significant melt in recent decades, and frozen ocean water, or sea ice. This year, the Arctic sea ice minimum almost reached a new record low. It was second only to 2012's extent, which was an anomalously low year in part due to unusual weather conditions. Sea ice shrinks and grows with the seasons. After reaching an annual minimum extent in September, Arctic sea ice begins to grow again as sea temperatures cool off for the winter. This year, Arctic sea ice had an unusually slow start to the regrowth period. In particular, the Laptev Sea, which is sometimes called a sea ice nursery because much of the Arctic sea ice initially forms there, was too warm for meaningful sea ice growth until much later in the season than usual. Oceans absorb heat from the sun, and our atmosphere prevents this heat from escaping back to space. The movement of this heat is one of the primary drivers of circulation and global weather patterns. We can measure the temperature of the ocean, and what we saw this year was unusually high surface temperatures across the Atlantic. The warm moisture that comes off the ocean acts as fuel to storms. So as this layer of the ocean gets even warmer, we're seeing that storms are becoming more and more intense over time. In fact, 2020 sea surface temperature contributed to an exceptional year in terms of Atlantic hurricanes. We saw 30 named storms, a new record, and 12 of these storms made landfall in the US. What's really interesting is that many of these storms intensified really rapidly. Not only are storms intensifying more quickly, but what we're seeing is that they're stalling near coastal regions more often, which is devastating in terms of floods and storm surge. While we're not 100% sure what is causing these storms to stall, it may have to do with climate patterns shifting in response to rising global temperatures. It's always really tough for a scientist to say any particular fire or any particular event was because of climate change. But we're getting to a point where we're starting to see season after season of record-breaking wildfire, season after season of really intense storms, that it becomes much easier to understand that this is likely the result of long-term climate change. In general, more heat means more energy in the Earth's system. So while 2020 was a significant year, it's important to know that this probably wasn't an anomaly of a year. We're likely to experience many similar years as the Earth's climate gets warmer. So while we saw a small dip in emissions this year due to COVID shutdowns, it was pretty short-lived. The vast majority of our greenhouse gas emissions come from things like electricity generation, which were less affected by the shutdowns than emissions from cars and airplanes. But we know that human activities have a powerful impact on our environment. Long-term strategies to curb human-induced climate change would have to focus on implementing cleaner technologies so we can reduce emissions without affecting people's daily lives. So while this is a story about heat, this is also a story about connections. Nothing on our planet happens in a vacuum, and our actions today impact our tomorrow. The choices we make now can make the difference between continued increases in greenhouse gas emissions and 2020 being the year that they peaked.